So in this lecture, let's actually illustrate and prove the main property that leads to obtaining a Fourier series representation in terms of Bessel functions. So again, this part usually I ponder whether to cover it or not. But again, in the name of practicing with manipulating Bessel functions in terms of integrating them or manipulating them in general, I think it's useful to go over this proof. Although we're not going to do the same proof for other boundary conditions, because you have to prove this orthogonality in all boundary conditions that come up. This is just for the boundary condition which the Dirichlet type that we met in the previous lecture. Another reason I want to go over this is because the book kind of does this proof in a different way. The book goes over the orthogonality property for a more general class of Sturm-Liouville problems. So it's an entire chapter on that one, which I don't cover it in its entirety. So then I chose to do this proof just for this specific case. If we have time, hopefully, when we move on to the last chapter on Legendre polynomials, which is a different type of equation and different type of solutions, in that case, I think I'm going to skip the proving the orthogonality property because it's more time consuming, I think. But let's do it in this case. Again, for practicing with computation, with involving Bessel functions, but also to reinforce what we really mean by this orthogonality and why that's important in the context of solving boundary value problems. So let's put together some of the stuff from the previous lecture. By alpha 1, alpha 2, alpha j, we denote the roots of the equation j naught of alpha c equals 0. So remember, c in this case denotes the domain for x. By the way, in the cylindrical coordinates, the notation for the variable is rho, but let's not be bound by that notation all the time. So x is the variable of this function, and the interval is 0, c, as it commonly appears in the cylindrical coordinates. So alpha j are the roots of this equation. The goal is to show that j naught of alpha 1x, j naught of alpha 2x, and so on, which essentially are the eigenfunctions, if you remember. The goal is to show these are orthogonal with the weight function x. So they are not going to be orthogonal by themselves. They are orthogonal via a weight function, which means, just to recall the definition of orthogonality with a weight function, that means if we integrate the product of any two of them and x, then that integral over in the interval 0, c, it's 0 if j is not equal to k, and not equal to 0 if j equals k. If you forget why we care about this, it's worthwhile to pause for a moment and go all the way back to lecture 6 in the beginning of the chapter to explain why we really need this orthogonality property to end up with a Fourier series representation in terms of these functions. So before we proceed with the proof, let's actually establish two differentiation formulas, which you know already, but in the context of the chain rule, so to speak. So we know that the derivative of j naught is going to be minus j1 of x. So these are one of those properties on Bessel functions. And another one, which we're going to use repeatedly here, is that x, j1 of x prime, so the product of these two, the derivative of it, is going to be equal to x j naught of x. Okay, so what you need to understand is that you can think of this as basic differentiation rules, and as with all basic differentiation rules, you can have a chain rule attached to them. So for example, let's say instead of wanting to compute j naught prime of x, let's say you need to compute j naught prime of alpha x. So let's say you have to differentiate j naught of alpha x. So you apply the same rule, okay, so that means minus j1 of alpha x, but you follow up with the chain rule, meaning that you multiply by the derivative of the inside, which is alpha. So if you have to differentiate j naught of a constant times x instead of just x, one ends up with not just minus j1 of alpha x, but minus alpha j1 of alpha x. This is nothing but the chain rule attached to the differentiation rules you have here. Furthermore, let's say I have to differentiate alpha x j1 of alpha x instead of x j1 of x. Again, the same rule applies. So you're going to have alpha x j naught of alpha x, but because of the chain rule, you have an extra alpha multiplied. And so notice here that because you have this alpha outside of any function, you can pull it out of the derivative. And in fact, you can cancel one alpha here. So that means you can write the derivative of x j1 of alpha x as alpha x j naught of alpha x. All right, so let's write this down separately here as two extra rules if you want. So the derivative of j naught of alpha x minus alpha j1 of alpha x, and the derivative of x j1 of alpha x, that's going to be alpha x j naught of alpha x. Because these modified formulas is what we're going to end up with when we deal with this proof. So let's start by showing that if j is not equal to k, let's start by showing that this integral is actually 0. So I'm going to denote this integral by I. Okay, so the integral from 0 to c of x j naught of alpha jx j naught alpha kx. The goal is to show that if j is not equal to k, then this will be equal to 0. Okay, so look carefully here on x j naught of alpha jx. I'm going to use this property over here, the second one, to write it in terms of a derivative. So if I move the alpha over, just replace alpha with alpha j, then x j naught of alpha jx is going to be 1 over alpha j, the derivative of x j1 of alpha jx, and j naught alpha kx dx. Okay, so carefully continue now with integration by parts. So integration by parts gives us 1 over alpha j x j1 of alpha jx j naught alpha kx evaluated between 0 and c. All right, we gotta go slow and carefully here, minus the integral from 0 to c, 1 over alpha j x j1 alpha jx times the derivative of j naught alpha kx. Look carefully here. When I take the derivative of j naught alpha kx, that's going to be equal to minus alpha k j1 alpha kx dx. All right, let's look carefully what happens here on the first part. When I plug in 0 for c, when I plug in c for x, I get j naught of alpha kc, which is equal to 0. Okay, remember where these guys come from, right? So j naught of alpha 1 c, alpha 2 c, alpha kc, and so on is equal to 0. So alpha j's are the roots of the equation j naught of alpha c equals 0. Again, it's very important to understand this part. This part is always confusing, and it's important in the computation to remember where these roots come from. So when I replace x with c, this becomes 0. When I replace x with 0, the whole thing becomes 0 again because x is a factor. Okay, so because of this, this part here ends up being 0. And let's clean up this a little bit. And we showed basically that the integral we started with is nothing but alpha k, the integral from 0 to c. We have a minus here and another minus inside here. They cancel. So the integral from 0 to c, alpha k over alpha j x j1 of alpha jx j1 of alpha kx dx. So you may wonder now, what's the big deal with this? All right, well, pay attention here. We just did this little trick, this integration by parts, by starting with replacing x j naught of alpha j with its derivative format. We could have done the same thing if we paired x with j naught of alpha kx. So we could do the whole thing all over again, but by writing x j naught of alpha kx as x j1 of alpha kx. So it is obvious that the same integral, if you proceed with starting with alpha k instead, would be written, would be equal to the integral from 0 to c alpha j of alpha k. So just interchange j with k, x j1 of alpha kx j1 of alpha jx dx. Just by doing the integration by parts in the same manner. So these two integrals represent the same integral, right? They represent the same value. So if I subtract the two, they should be equal to 0. Okay, so if I subtract the two, and these are the same because the multiplication is commutative, so j1 alpha j, j1 alpha k, same thing here. I can put it out. So if I subtract the two, I end up with the integral of alpha k over alpha j minus alpha j over alpha k j1 alpha jx j1 alpha kx dx equals 0. So if you look carefully here, this guy is not equal to 0 if j is not equal to k. Right? If you come up with the common denominator, you end up with alpha k squared minus alpha j squared on the top, which is not equal to 0 again if j is not equal to k. But if this integral is 0 and this constant is not equal to 0, that means, and let's see if we can write it in the same piece of paper so we have it in front of us. That just means, oops, got overexcited here and hit the camera. So that means the integral from 0 to c j1 of alpha jx j1 of alpha kx is equal to 0. But if you go all the way back here, so x in front of it, I forgot the x here. There was an extra x. Okay, so the integral from 0 to c x j1 alpha jx j1 alpha kx equals 0. And all the way, if we go all the way back to either this or this, pull up the constant, that just means your original integral is equal to 0. So you simply write the same integral in two modes, and when you subtract the two and set it equal to 0, you conclude that in fact the integral of just x j1 of this j1 of this is equal to 0, which means your original integral that you started with is equal to 0. So you just proved that essentially the first part of the orthogonality property, namely that this integral should be 0 if j is not equal to k. So the second part is slightly more trickier, but it can still be done in a short amount of time. So let's stay tuned for the second part to show that the integral is not equal to 0 if j is equal to k. And then finally, maybe on a third part, we just conclude with how to write a function in terms of a Fourier series representation involving Bessel function. So stay tuned for the second part.